Hey everyone, and welcome to my VHDL guide. In this video I will be going through the necessary steps for getting VHDL up and running on your system. We will conclude this guide by designing a simple logic circuit and simulating it. All the links, code and commands that I used in this guide are listed in the description below. However, I highly recommend that you follow along and type everything yourself. It will really help you out in the long run. I do want to point out this guide is specifically for Windows. If you're on a Linux machine, click here to check out my Linux version of this guide instead. So, let's get started. The first thing you should make sure you have is a source code editor. I do not have one installed on this machine, so I'll go ahead and install Notepad++. So if I Google Notepad++ and I go to the website, go to download, and I'm going to click on the Notepad++ installer. We're going to show it in a folder, so when it's complete. And there we go. So we can close Chrome. And let's install Notepad++. Yep. We want it in English. Next. I agree. Next. And that looks good. Let's put a shortcut on the desktop. Yep. And there we go. And we can close that. And we can delete the installer. Now that we have a source code editor, we need to get a VHDL compiler and simulator. For this guide, we'll be using GHDL, which is a free and open source VHDL compiler and simulator. So let's go ahead and Google GHDL and scroll down to the GitHub code repository, and then you want to go directly to the releases link, and you want to scroll down to the latest release, and then you want to find the file that is Win32. That is, it says GHDL dash whatever the latest release is dash Win32, and let's go ahead and download it. Now the reason you're downloading the Win32 file is because these are the pre-compiled binaries for Windows. That is, they've already compiled it for us and we can just unzip it and it's ready to go. In addition to the compiler, we also need a waveform viewer so we can inspect the output of our VHDL simulation. For this guide, we'll be using something called GTKWave, which is actually part of the GEDA software suite. Now, when you Google it, you don't want to go to their custom SourceForge website. You actually want to go to their SourceForge project website. I will have the link in the description below as well. Once you're on the project website, you want to go to Files, and you want to scroll down to the latest version which they have Windows binary for. In my case, it is 3.3.71-bin-win32. Now, this is the important part. You want to download the bin-win32 because just like the GHDL, this is the pre-compiled binaries for Windows. So these are ready to go. Once we download them, we can unzip them and it's ready to go for us. So let's go ahead and download it. Now that we have both programs downloaded, let's go ahead and extract the two zip files. So let's extract the GHDL and let's go ahead and extract the GTKWave as well. So I'm just extracting them to our download directory. Now let's go to our Start menu, let's go to File, and then go to this PC and go to your local disk, which is probably your C drive, and in there what I like to do is I like to create a directory for all our design automation tools. So let's call it EDA for electronic design automation, and this is where I put all my programs, and you can put these two programs in any future program that you might have. So go ahead and drag the GHDL compiler directory over there, and go ahead and drag the GTKWave directory over there. Now go ahead and rename the GHDL dash whatever version to just GHDL, so they have two consistent names, and you can go ahead and delete the zip files that you have downloaded. While GHDL and GTK are the only two programs I will be using in this guide, there are actually quite a few other EDA tools out there. If you check out some of my other videos, you'll find some guides on tools you can use to design circuit boards and tools you can use to draw logic design and schematics and even turn them into functional VHDL code. So there are a great number of other tools out there you can add to this directory later on. We need to do one last thing before we can use the programs we've downloaded, and that is updating the path environment variable with the location of our new tools. The reason we want to do so is so we can seamlessly use our tools from the command prompt. To do that, let's go to our Start menu and let's go to Settings. And inside our settings, you want to go to the Find a Setting and you want to just type ENV. And it will already find you the two possible options. You want to go to the Edit the System Environment Variables, which should open you the System Properties window, and it should open the Advanced tab, and you want to go down to the last button that says Environment Variables. Once you're here, you want to search for Path under System Variables. Once you find Path, you want to go to the Edit button, and then you want to go down here and you want to click on New. Now for some reason, if you don't type anything, you can't type Browse. So I'm just going to type A, I'm going to hit Enter. I'm going to click on the New button again and I'm going to type B and I'm going to hit Enter. Now once I have A and B in here, I want to go back to the Browse button and I want to go to this PC. And essentially I want to navigate to the C drive and to my EDA directory. I want to go to my GHDL directory, and then I want to select the bin directory. Once I have the bin directory selected, I just want to hit OK. So what you should see when it's all said and done is you should see the path to your bin directory for the GHDL compiler. So in my case, it's C/EDA/GHDL/bin, and that's what you want here. Now I'm going to go to the B entry I've created, and once again I'm going to go to Browse and I'm going to navigate to my EDA directory once again, and I'm going to select my GTKWave directory this time, and I'm going to select my bin just like I did with the GHDL. So when it's both set and done for both of them, you should see the two bin directories for the two programs. Now if in the future you want to download and install additional programs, I highly suggest that you follow this and you add them in here, because whenever you go later on and start typing commands in your command prompt, these commands will show up in there, as you will see in a few minutes. So once you have both of these paths set, you want to click OK, and then you want to click OK again to close the environment variable, and then we want to click OK again for the system properties. And we can go ahead and close the settings. Now that we have all our programs installed and set up correctly, let's go ahead and test them out. So I'm going to create a working directory for my code, and I'm going to call it half-adder. And I created it on my desktop. You can go ahead and create it wherever you usually save your code. And then I'm going to go to my Start menu, and I am going to type cmd.exe, and I'm gonna hit enter, and this opened up the command prompt. And then I'm going to navigate to my half adder directory. Now, since I placed it on my desktop, I'm going to cd to my desktop. Oops, desktop. And then I can type dir to list the files on my desktop. And then I'm gonna cd once again to my half adder. Now I can type half and hit tab, and it will auto complete it for me. And then I can type cls to clear the command prompt. Now if I type dir, we're gonna get an empty directory, and all our code is gonna go in here. So let's go ahead and open my Notepad, and the first thing I want to do is I want to go to language, and I want to go to V, and I want to go to VHDL. So I have a syntax highlighting and very simple autocomplete for my code. So the first file we're going to create is the actual half adder. And we always start out by specifying that we want to use the IEEE library, and specifically we want to use the IEEE std logic 1164.all. And the IEEE 1164 package contains all of our standard logic signals. So that's why we specified, because we want to use it. Now let's go ahead and create an entity, and we're going to call it HA for half adder is, and then we're going to go ahead and end our half adder entity. And inside the entity, I'm going to create a port map, and we're going to put in there our input and output signals. So we have two inputs, which is A, and that's an input, and it is an STD ulogic signal, so it is a 1-bit signal. And then we have our B, which is also a single bit signal. And then we have two outputs. One of them is a sum, and I'm going to call it O for output. And then it is also a single bit signal. And then we have our carry out, which is also an output, and it is also STD ulogic. So we have two inputs and two outputs. And I'm in the habit of saving all my stuff automatically. So we have two inputs, A and B, and two outputs. And let's go ahead and actually save it. And I'm going to go to my desktop, and I'll go to my half adder, and I'm going to call it ha.vhdl. I'm going to hit enter. So it is saved here. And if I go to my command prompt and hit the up arrow and type dir, I can see that my file is in here as well. Now let's go ahead and describe the actual behavior of this entity we've created. So we're gonna define architecture, and let's call it behave of our half adder is, and then we want to begin a block, and we want to end behave. Now inside our behavior, we want to define the behavior of this half adder, and the half adder is a very simple device. So we know that the output is 1 whenever A is 1 or B is 1, but not when both, because when we add 1 plus 1, we get an output of 0, and we have a carry out. So we're going to say that our output is A, X, or B. That is, it is when A is 1 or B is 1, but not when both are 1. And then our carry out is quite the opposite. It's exactly when A and B are 1. So let's go ahead and save it, and now we have the complete code for our half adder. But before we go on, let's go to our command prompt and check out that there are no syntax errors in our program. To do that, we can call our GHDL compiler and we can specify the -s option, and then we can give it a file which is halfadder.vhdl and hit enter. And what the -s option does is it does a syntax check on our file, but it doesn't compile anything. So it's just a simple syntax checking, and you will see that it tells us that on line 12 we're missing a semicolon at the end of our port clause. And that is correct. In here, at the end of a port clause, we did forget to specify semicolon. So if I put the semicolon and I click save, and I go back to my command prompt and click the up arrow to bring up the previous command and hit enter, you'll see that now there are no errors in my code. So this code is done, but we do not know whether it's actually correct. Now let's go ahead and simulate our half adder. The way we do that is by creating something called a test bench. So let's go ahead to Notepad++ and create and click on new. And we're going to create another file which is going to be a test bench. So let's start out with our declaring that we want to use the IEEE library, and let's go to Notepad++ and specify that our syntax is VHDL, and we want to use once again the IEEE.stdlogic1164.all. So once again we're using the standard signal package, and we're going to create another entity, and this time it is going to be our HA_TB. This is, by the way, a very common naming convention. The naming convention people typically use for test benches is the UUT, which is the unit under test, followed by underscore, followed by TB. If you're using, later on, if you discover some of the bigger, more extensive integrated development environment, for example, the ones offered by Altera or Xilinx, they actually generate some of that code for you, and they will typically have the same naming convention, which is the unit under test, which in our case is the half adder, followed by an underscore, followed by TB for test bench. And we're gonna continue with is, and then we're gonna just write and then we're going to close our entity block. And you'll notice that our entity block has no signal, so there is no input or output signals going into or out of our test bench, and that should make sense because a test bench is a complete unit. It will go ahead and send signals to a half adder, and then it's gonna read back those signals, and then we're gonna check out whether these signals are correct. So we don't have anything going in or out of the test bench because we don't need that. So let's go ahead and save our test bench, and I'm gonna follow the same naming convention, which is HA_TB.VHDL. So notice if I do dir here, we'll see that I have my half adder, and then we have our half adder test bench. Now we need to actually define the behavior of our test bench. So I'm going to start with architecture, and then I'm going to call it test of HATB is, and then we close the block with end test. And inside the architecture, we're going to first tell VHDL which components we're actually going to use. So we're going to tell it component, and then the component we're using is a half adder, so HA, and then end component. And inside, we have to give it the very same signals that go in and out of a half adder. So in order to not make any mistakes, I am going to verbatim copy the port claw, and I'm going to paste it right into my component list. So I do that so that I do not make any mistakes when it comes to the signals that come in and out. Note that these two signatures have to match. If they do not match, you're going to have a problem later on. So I find that the easiest way to do that is to simply verbatim copy it in there. Under our component, I'm going to create a number of signals that I'm going to use inside my test bench. So I'm going to say signal, and then I'm going to name it the very same signals that are going to go to my half adder. So I'm going to call it A, B, and then let's call it O, or O, and the last one is C, and they are all STD ulogic. Once again, they're all single bit signals. And we want begin, and this is where we're going to describe the behavior of our test bench. So first, let's create a port map, and let's call it half adder, and we're using our half adder component. We want a port map, and we are simply connecting our A wire to the A input on a half adder. We're connecting the RB wire with the B input in a half adder. We're connecting the O wire to the output of the half adder, and we're connecting the C wire to the C output of a half adder. And then we completed. So essentially, we're connecting this wire to this input, this wire to this input, this wire to this output, and this wire to this output. And the reason we're doing that is so that we can deliver signals on the A and B inputs, and then we're going to read out the output from O and C to verify that our half adder is actually functioning correctly. So let's go ahead and create a process. The reason we're creating a process is so that we can deliver signal sequentially and not concurrently. So we have a process, and let's type begin, and then we close the block by saying end process. And inside our process, we're effectively going to deliver a test. Now, for the purpose of this guide, I am not gonna write anything too complex. Ideally, you wanna create some kind of a test that will exhaustively, or as much as possible, test all your values and make sure that it is correct. For our purpose, since it's such a simple component, I will manually do that. So initially, I'm gonna start out by delivering an unknown signal to A and an unknown signal to B. So we're gonna start out with both inputs being unknown. And then for the purpose of our simulation, we're gonna wait for 1 nanosecond. And then after 1 nanosecond, I'm gonna send a 0 to A and a B, and we're gonna send a 1 to B. So we're gonna send a low to A and a high to B, and then we're gonna wait for another 1 nanosecond, and then I'm gonna send a 1 to A and a 0 to B, and we're gonna wait for 1 nanosecond once again. And finally, the last test we're gonna do is we're gonna send 1 to A and 1 to B. So that's when we are adding 1 plus 1. So effectively what I'm doing is The first test I'm running is I'm giving it unknown. The second test I'm giving it is 0 plus 1. The third test is 1 plus 0. And finally, the last test is 1 plus 1. So we have effectively exhaustively tested every single input. And I'm going to wait for 1 nanosecond again. Now, because this is the last test, I'm going to put in here an assert. And I'm going to just specify false so the assert evaluates. And I'm going to report, let's say, reached end of test. And then we're going to put in here a final wait, so it knows it's going to wait forever effectively. So once it executes all these tests, it's going to print out reached end of test, and then it's just going to end our test bench. Before we go on, let's go back to our second test and let's add one more test, which is when A is 0 and B is 0. So we were missing one test in here, and we're going to wait 1 more nanosecond for that one. So now we have another case, which was when they're both 0 and 0. So now that we have our test bench complete, let's go back to our command prompt, and I'm going to type CLS to clear the screen once again. And let's type dir, and you'll see that we have our 2 files in here. So we have our half adder, and then we have the half adder test bench. Now I'm going to go ahead and I'm going to analyze a half adder. So to do that, we're going to type GHDL -A and then the name of the file, which is ha.vhdl. I'm going to hit enter. If you get no messages, it means that everything went through and it's good to go. If you get some kind of an error message, it probably means that you need to fix something. So in my case, I have no messages, and you shouldn't have one either. And now let's go ahead and analyze our test bench as well. So we're gonna do GHDL -A, and then we're gonna do HA_TB.VHDL and hit enter. And this analyzed our half adder test bench as well. So once again, no error messages, so we're good to go. And now we want to actually execute our test bench. To do that, we use the E switch, which stands for elaborate. So elaborate switch will build our executable. So we want GHDL, and we want -E, and we're going to give it our test bench that we want to elaborate. Now notice that because we already analyzed our VHDL, when you specify the elaborate, you tell it which object or which unit you want to elaborate. So in our case, I'm going to tell it this is the half adder test bench. And notice that we're not giving it a file, we're just telling it which unit we want to elaborate, which in our case is this test bench entity that we've created. So I'm specifying only the name of it, and I'm going to hit enter, and you see that it went through and no messages. So we're good to go. Note that GHDL already knows to look in our directory for the files it already previously created, and it will find what it needs to find to get the job done. Now that we went through and we actually created our compiled simulation, we want to execute our test bench, so we want to run it. And to do that, we type GHDL-R, and once again, we only give it the name of the object we are running, which in our case is the half adder test bench. And I'm going to hit enter, and it ran through my test bench, which are these tests, and notice that it reached line 44, and then it says that assertion error reached end of test. And that is okay because that is something that I gave it. So I gave it an assertion to say that when we reach this point of our test bench, I know that it went through everything and it's done. And then I gave it a report message that said reached end of test, which is what it printed. Ideally, your test bench will have all kind of checks in there to make sure that your logic worked. And if it detects some kind of an error, ideally you want to report it so that you see it in your console. For the purpose of this guide, I didn't add any actual checks in there because it's so simple that it doesn't make sense to do that. Instead, we're going to verify the unit using a waveform viewer. And to do that, I am once again going to use the up arrow to go back to the last command I used, and I'm going to add another option to the end of my command, and that is a -- VCD equals, and I'm going to call it half-adder.vcd, and I'm going to hit enter. And notice that it ran the very same simulation. However, what this switch does is it tells GHDL that not only I want to run my half-adder test bench, I also want to generate a dump, a VCD file dump, and the name of the file that I want you to dump into is half-adder.vcd. Now, a VCD file format is a special file format that can be used with a waveform viewers to check out your waveform. So if I type dir, you'll notice that it created another file in here called half-adder.vcd. And that is our waveform that we want to check out. And to do that, we're going to use our GTKWave program that we've also installed. So I'm going to do GTKWave, and I'm going to put a space, and I'm going to specify the half-adder.vcd. So I'm going to give it our waveform dump. And I'm going to hit enter, and you'll notice that the waveform opened up. And I'm going to move it a little bit here, and then I'm going to move our test bench to the corner a little bit. And this is GTKWave, and it's a waveform viewer. And the first thing you want to do is you'll notice that it has a half-adder unit here, and the signals are down here. And what you want to do is you want to drag the signals you want to see in the wave viewer. So in our case, we want them all actually. So we want our two inputs, which is A and B, and then we have our sum output, and then we have a carry out. And now you'll notice that by default it opens up with 1fs, 2fs, 3fs, etc., etc. Now fs stands for femtoseconds. That is, it's 1/4 of a second, or 10 to the negative 15 seconds. So it is a really, really small unit. It is so small that in our simulation we gave it a resolution of 1 second wait period. So femtoseconds is way too small. So we want to actually zoom out. To do that, I'm going to press and hold down the control button, and then I'm going to use my mouse wheel to scroll out. And as you scroll out, you'll scroll to a higher and higher, to a lower and lower, essentially, resolution. So notice that now we are in picoseconds, but we want to zoom out even more. So we want to zoom out to nanoseconds, and there we go. Notice that now we're working with nanoseconds, which we can actually see our test simulation. And notice that for the first test, we start out by specifying that both inputs are strong unknowns. And you will see that when I click between 0 and 1 nanoseconds, you'll see that our inputs are unknown, and obviously our output and carry out is irrelevant, but it's also unknown. After 1 nanosecond of wait, you'll notice that it changes to the next test that I gave it, which is A0 and B0. Now when we add 0 plus 0, we get an output of 0, and we have a carry out of 0 as well. So we know that, hey, this works. Next, we're going to go to our third test, which was 0 plus 1. So you notice that A0, and then we have B is 1, and then the output is correct, 1, and then we have a carry out of 0. So 0 plus 1 is 1 with a carry out of 0. Next, we're going to move to sometime between 3 and 4 nanoseconds. And you'll notice that this is our fourth test, which is 1 plus 0. And 1 plus 0 is 1 with a carryout of 0. So this is also correct. And then our final test is 1 plus 1. So if I move to sometime between 4 and 5 nanoseconds, you'll notice that this time we have our signal set to 1, and B is also 1. And when we have 1 plus 1, our output is 0, and then we have a carry out. So when we have 1 plus 1, we have a carry out of 1 and an output of 0. And therefore we know that our half adder code is logically correct. And that is all for this guide. This is it for this guide. I hope you were successful in following along and getting everything to work correctly. If you got stuck on anything or you have any questions or comments, do leave a comment below. I will try my best to answer them. If you're interested in additional guides, please do check out my other videos in my channel. And finally, don't forget to like and subscribe. So, thank you.